today we're going to start talking about dynamic programming. And so really we've talked about two algorithm design paradigms so far, divide and conquer and greedy algorithms. And this is the third one that really encompasses a lot of different problems and a lot of different algorithms. And once you get good at seeing dynamic programming solutions, it can be a very powerful tool for a lot of different problems. Now, once I show you some examples, you'll still not understand why this is called dynamic programming. It goes back to the 1940s or 1950s, and it had some meaning back then, but now it really doesn't really have much meaning in terms of the word programming anyway. So we just call this DP. The general technique is DP. And the way I'm going to introduce this is through a generalization of one of the scheduling problems. So now imagine you have a set of intervals, and each interval has some weight associated with it, some number. This is 5, 3, 5, 4, 7, 1, 6, whatever. These are values or weights, costs, whatever you like to interpret them to be. And the problem now is to pick a subset of intervals that are pairwise non-overlapping. That's what we looked at before. We didn't want overlapping intervals. That was in the first scheduling problem we looked at. But now, instead of maximizing the number of pairwise non-overlapping intervals, we want to maximize the total sum of the values that are associated with the intervals. So we're given, I'll call them weighted intervals. So interval I has weight or value VI. Okay, so this is just some number associated with interval I. So here's an interval, its associated value is 7. Here's an interval, its associated value is 5. And given weighted intervals, interval I has weight VI. And our problem is find a subset of pairwise non-overlapping intervals whose sum of weights is maximum. Okay. So just looking at this example, well, taking the one that's 7 might be a good idea, but you could also achieve that with 1 and 6, but that's probably not a good thing to do because 6 is out there further than 7. So it looks like taking 7 is a good thing to do, and then probably one of these two 5s. You can't take the 6. Taking the 3 blocks both of the 5s. So just looking at it, eyeballing it, it looks like 7 plus 5, 12 is the best total sum we could get here, picking non-overlapping intervals. And you can make up all kinds of stories about what this problem is modeling in some real-world situations. These are jobs that are available to you. They have a starting point and a finishing point. And you can't do more than one at a time. And the number here is how much you get paid or the value for doing that job. And so you want to maximize what you earn. And so that's the origin of this problem. If these were costs and you were trying to minimize your costs, what would you do? Based on this problem, if I said pick a set of non-overlapping intervals to minimize your total cost?
You just search for the smallest one and just have that.
You could search for the smallest one, but you could even do better than that, unless the costs were negative. But Do nothing, yeah. Okay, so the minimization problem, at least with positive costs, it doesn't seem meaningful. But anyway, so that's why we're maximizing here. And in terms of the original problem that we had where we wanted to pick the largest number of intervals, what does that correspond to in this framework? We're just trying to maximize the number of non-overlapping intervals. Yeah?
If all the weights of the intervals are 1?
Yeah, if you set all the interval weights to 1, then the total weight or total value you get is just the number of intervals that you would get. Okay, so we have this problem. And remember before, when we were just trying to maximize the number of intervals that we took, we sorted the intervals according to their n times, right? And so to maximize the number of intervals chosen, what did we do? We sorted the intervals by their finish time. And then examined the intervals in that order. And I won't write down exactly what we did. But just remind you that we sorted the intervals according to their n time, and then looked at them and in that order, and in the order of smallest n time first, and we just excluded any of the intervals that overlap the one that we took. We took the first one with the smallest endpoint first, and then continued in that way, and that we proved was actually optimal. Well, what if you do that in the weighted case? Okay, you just sort them by endpoint, and then again you take them the first interval, the interval with the smallest endpoint, and then exclude everything that overlaps it, and then continue recursing that way. Would that give you an optimal answer? An optimal total weight? I'll ask it in two contexts. Will it give you an optimal in this example? And will it give you an optimal in general?
Yes, no.
Yes, no, exactly. Yeah, this example, it turns out, the algorithm that would maximize the number also happens to maximize the weight in this case. This would be the first one you would take. If we were just trying to maximize the number of intervals taken, you would take this, you would exclude those, you would take this, you would exclude those. And so therefore, by this example, you can extrapolate that it always gives you the optimal total also, right? No, not right. So if we change this, for example, to 1 and change this to 7, then clearly this 1 plus this 5 is not the optimal. You could take 7 and this 5, for example, and get 12. So this problem of maximizing the total weights looks more complicated than the problem of just maximizing the number of intervals. And so we'll need another type of algorithm that isn't quite so greedy. It isn't just left to right, pick the next available interval and then exclude the ones that are intersecting there. So in these kinds of problems, you start thinking recursively. Okay, you set up some notation and think about the problem recursively. That's the way one begins with a dynamic programming approach to problems. So let me define opt of j is the value of the optimal solution using only or restricted to intervals 1 through j. And here I'm talking about in the sorted order. Okay. So just intervals 1 through j, and so initially, what's opt of 1? Okay, opt of 1 refers to the value of the optimal solution using only intervals 1 through j. So you have a subproblem of finding the best set of non-overlapping intervals, of maximizing the total weight or total value of those intervals, but only considering intervals 1 through interval j. So now I'm asking, what is opt of 1? So if you only consider interval 1 through interval 1, what's the best you can do? Yeah, just take interval 1. There's no issue of overlapping. So, and well, we've assumed that these are positive weights so that you get some value out of that. And so opt of 1 is just 1. Or opt of 1 is equal to the value you get from interval 1, or the weight from interval 1. That's V1. Okay, and what is it that we want? We want eventually, if there are n intervals, okay, eventually, in terms of this notation, what is it we're trying to compute? Just using this notation, what's one of the things that we want to know? We satisfied with opt of 1? Opt of 2? What is it we want, ultimately? Right, opt of n. Who said that? Oh, I did. Yeah, we want opt of n, because that's 1 through n. That's everything. Okay? So I'm just trying to use the notation here, use the terminology, so you're comfortable with it. Opt of n is the value of the optimal solution it uses, that's available to it, available to the solution, intervals 1 through n. Okay? Not that you're actually including all those intervals 1 through n in the solution. They still have to be non-overlapping. But those are the ones that you could consider using 1 through n. All right. So now that we have notation, we now want to set up a recurrence. We want to talk about this problem recursively. So we want to express a solution for opt of n, or a way of, I'll call it just in general opt of j, a way of figuring out what opt of j is recursively. So what does that mean? It means saying something about what opt of j is in terms of opt values for subproblems. Well, what are the natural subproblems? Those are the problems where the value here is less than j, because we defined, our definition here goes essentially from smallest, well, it goes from 1 through j. So it's going left to right in terms of the intervals, in terms of the endpoints of the intervals. We want to express a solution for opt j recursively. So opt j. So let's draw a picture to try to, here's interval j, okay, and here are all the other intervals, 1 through, I guess this is interval 1, and this looks like interval j minus 1, okay? So those are the intervals 1 through j. So thinking about the optimal answer you could get, or the optimal value you could get if you use the intervals from 1 through j, and thinking about this recursively, there are many different ways of doing that and thinking about it, but one way is to think about, is just to focus on j. That's the last interval that's under consideration. And there are two things that can happen to interval j in the solutions. Solutions are subsets of intervals that are pairwise non-overlapping. There are those solutions that contain j and those solutions that don't contain j, right? So if we want to get the best solution over all possible sets of pairwise non-overlapping intervals, we can break it into two cases, the ones that contain j and the ones that don't contain j. All right? So let's take the ones that don't contain j. So we're just saying, think of all the subsets of intervals that are pairwise non-overlapping and don't contain j. What's the best possible value of those kinds of solutions? What's the terminology or the notation for the best possible value you can get for those kinds of solutions? You're not going to use j. Anybody else? Yeah.
It'll be just like opposite j minus 1.
Right. Okay. So one possibility is opt of j minus 1. And this comes from don't choose j. Okay? That's one of the two possibilities. What's the other one? Well, the other one is we're going to use j. All right? But now if you use j, you pick j to be in your subset, then you can't use any of the intervals that overlap j. Those are all excluded. So we're thinking recursively. We're thinking, what are we going to do with interval j? If we take it into our solution, then everything it overlaps is excluded in that solution. So what are the ones that are permitted? Well, pictorially here, if we just look, this looks like the interval whose end point is as far as possible, is as late as possible, but it's before the start of j. Okay? So Si, it doesn't overlap. That's right, this is j. Start of j, end of j. This is the finishing point of this interval, whatever this interval happens to be, and so on. So just pictorially, what intervals are available if you take j into your solution? What other intervals are possible to consider? It's this interval and everything before it in our ordering, in our sorted ordering, because you cannot allow any interval that intersects j. So it's this interval and everything that finishes before it. So it's useful to have a notation for that. So P of j is equal to the interval I, or the index of an interval. Let me call it index. Index I, such that, first of all, I is less than j, and the finishing time of I is less than the starting time of j. So that means they don't overlap. Okay? So the finishing time of I is less than the starting time of j, and I is less than j. So these two together says that they don't overlap. And I, yeah, it's easiest to do it this way. It's the largest index such that this is true. Okay, and this is in the sorted order. So we've sorted the intervals and we've given them numbering 1 through n based on their ordering in that sorted order. Okay, so this is language for the previous, or p of j, is the largest index I, such that I is less than j and the finish time of I is less than the started time of j. It just means that's the interval whose ending point is as far right as possible among all of the intervals that start before j does, or finish before j does, and don't overlap it. Okay, so a lot of words for the same thing I put up here in terms of a picture. All right, so back to the second case. The second case, which is we're looking for solutions, we're looking for subsets of intervals that are pairwise non-overlapping and that do include j. Now, if they include j, then what's their value? Well, you get the value of j, okay, because you're taking j, so you get its value. And then you get some values from some other intervals that don't overlap j. And you want to get the best possible sum of values, or the best sum of values possible, okay, among what's allowed. Can anybody tell me how you express that? What's the notation for that? Yeah?
Plus opt I.
Opt I, yes, in terms of when I called this an I, but what's I more generally? In terms of j, yeah. It's p of j. So this is getting cramped in here. I'm going to rewrite this a little more tightly. This is opt j minus 1, and this is vj, the value you would get from taking interval j, plus the value, the best possible value, you would get when you consider intervals 1 up through interval pj. Pj depends on j. Okay? In this picture here, it was this I, but generally it's pj. Okay, so this interval pj depends on j. Does everybody see that? This is the critical point in terms of understanding this recursion. That if you take j, the only other permitted intervals you can take, if we're considering intervals from 1 through j, are the ones that don't overlap j. And notationally, those are the intervals, a subset of the intervals that don't overlap j are the intervals from 1 through pj. Okay? So intervals 1 through pj don't overlap j. So these are the two possibilities. Either you don't take interval j into the solution, or you do take interval j in the solution. And the best you can do if you don't take interval j is that, and the best you can do if you take interval j is this. Okay? And since these are the two possibilities that cover everything, what is opt of j? Yeah.
Max of either.
Yeah, it's the best you can do over either of those. It's the max of those. So here we have a recurrence, or I'll call it recurrence, that tells you recursively what opt of j is. It's recursive because it's talking about opt of something else. So it's not, well, when we were solving recurrence relations, it wasn't in what we were calling a closed form. But here, at least it's telling you prescriptively and recursively how you could find it. Okay, now there is a subtle point, and most discussions of dynamic programming pay attention to this, but and I'm going to, it's probably something that nobody has thought of. It's sort of, it's too subtle. Anyway, I was about to say, if I confuse you with what's coming, just ignore it. But now I've already confused you, so I shouldn't have said that. All right, here's the subtle point about the correctness of dynamic programming. In this case, we said if you take interval j, well, you get its value, fine, vj. And then the best thing you can do, having taken interval j, is whatever value is given to you by opt of pj. Well, certainly taking some non-overlapping set of intervals, pairwise non-overlapping set of intervals between 1 and pj, you can add those together with interval j and you get a set of non-overlapping, pairwise non-overlapping intervals. That's by the way we defined pj. But why is it right to say opt here? Well, if you consider any other subset of pairwise non-overlapping intervals in the range 1 through pj, if their value wasn't equal to this, then you could do better by taking that subset whose value is this and adding it to vj. And that's essentially a proof that it was the right thing to do is to take the solution whose value is opt of pj. Okay. Does that seem like a totally silly and trivial thing to stop and point out? Maybe it seemed just so totally natural that of course it would be opt of pj. But in the world of dynamic programming, that's usually, people make a big point about that. And this is what's an instance of what's called the principle of optimality. So if that was confusing, just ignore it. If this seems totally right and what I was saying was confusing, then again, just ignore that. Okay, so we have this, now we have this recursive expression for what opt of j is, and we know what we want is opt of n. All right, oh, we should also maybe, well, we actually did. We already have the base case. So we've got a base case. We have a general recurrence relation. We know where we're going to eventually. So we really have all the components for a recursive solution to this problem, at least a recursive solution to computing the value. Now, eventually we want to know what the actual intervals are. But right now we're focusing on the problem of computing the optimal value, and then later we'll talk about how we actually get the intervals that are associated with that solution that gives you the optimal value. Well, with this, let's say I stopped right now and I said, everybody get out your laptops and write, you have 5 minutes to write a program that can compute opt of n, what would you do? Well, you'd complain because a lot of you don't have your laptops. But okay, besides that, how would you write that program? What would you do? What's the most natural thing to do at this point? Okay.
Just take the relation, the recurrence, and write it with an if and try to get the maximum.
Okay, you certainly can implement this recurrence. The max would be just compare this value and compare this value, whichever is the largest, take that one. But what's the superstructure of the program?
It's a recursive call.
It's a recursive call, and so therefore what's the first call?
N.
Opt of n. Yeah, you could write this as a program, and that's a triviality. You have an if statement, you compare these two things. And then as a recursive program, you would then call it with opt of n and let the recursion finally figure out what the value was. You have the base case, so that's okay too. I mean, I could try to write pseudocode here just to point out explicitly what I'm talking about here. So this is opt j, I'm calling opt j. If j equals 1, return v1, else compute, well, if opt j minus 1 is greater than or equal to vj plus opt pj, return opt j minus 1, else return vj plus opt pj. And, I said 5 minutes, and I've just finished it. Of course, it's not an actual program, but I mean, it's just triviality to write this as a recursive program. Here's a recursive call. Okay, opt j minus 1, it's implicit that we're calling opt again, but now it's with j minus 1. Here we're calling opt with pj. Of course, I really, in terms of a real code, I should have to figure out what find pj. All right. Anyway, everybody should be able to turn this into a real program now in 2.5 minutes. Okay, so this is certainly straightforward. But is it efficient? Is this what we would be happy with? So let's just think about maybe a little example here. Maybe that's enough. So this is interval 1, 2, 3, 4, 5. And so initially we'd be calling opt of 5. Okay? And it will call opt of 4. That's the opt of j minus 1 call. And it'll also call what? If you look in here, we have this is the opt of j minus 1. Here we need vj plus opt of pj. What's pj in this case?
3.
It's 3. So this would call opt of 3. And then opt of 4, what does it call? It calls opt of 3. Okay. And also it calls what? It has to call 3, opt of 1. And what does opt of 3 call? Well, again, using the recursion, or that version of it, it calls opt of 2. And then, again, opt of 1. Okay. Well, we just said what opt of 3 is. It's opt of 2, and then opt of 1. Okay. And then opt of 2, what does it call? It calls opt of 1. Opt of 2. Yeah, well, it's either 2 or, okay. Or it just gets v2, whatever. v2 or opt of 1. Okay? So the recursive calls, the tree of recursive calls would be something like this. Now, how many recursive calls is that? Well, I mean, in general. Suppose we went out to n, and it's the example where each interval I overlaps I plus 1, but not I plus 2. Okay, so every interval overlaps the next interval in the sorted order, but doesn't overlap anything else. No, that's not true. It overlaps, each interval is overlapped by the one before it and overlaps the one after it. So we have this little staircase, cascade. Yeah?
Shouldn't opt of 4...
Is what?
Shouldn't opt of 4 call opt of 3 and then opt of 2 instead of 1?
Opt of 4, oh yeah, you're right about that. That's true, yes. Opt of 2, and so yeah, so we even have another business in here. Yeah, thanks. But okay, but can anybody see in general what's happening here in this little example? Well, each opt of j is calling opt of j minus 1, and it's also calling opt of j minus 2. Okay, just the way these things are overlapping. And this is just setting up the example so that pj is always j minus 2. So p of 5 is 3, p of 4 is 2, etc. So we can have many of these. Okay? So opt of j calls opt of j minus 1 and opt of j minus 2. Does this remind you of anything? Rabbits? Did I hear rabbits? No. What?
I was going to say the Fibonacci series.
Fibonacci series. And what does Fibonacci series remind you of? Rabbits. Okay. If you don't understand that, Google it later. Okay. So the Fibonacci series, which is f of j equals f of j minus 1 plus f of j minus 2, that's the Fibonacci series. That's the general recursive description of the Fibonacci series. Okay, here we're saying how many calls, we're considering, how many calls will it take to compute opt of j? Well, it's however many calls it takes to compute opt of j minus 1 plus however many calls it takes to compute opt of j minus 2. Because that's what's happening. When opt of j calls opt of j minus 1, that spawns additional calls, and opt of j minus 2 spawns additional calls. Okay? So the number of calls that it takes to compute opt of j is expressed by the Fibonacci series. So in fact, the number of calls it takes to compute opt of n is equal to the Fibonacci number of n. Or some, I may be off by the base case or something, but essentially it's growing like the Fibonacci number. Okay? I'll just put a little twiddle here to say that it's essentially the Fibonacci number. I mean, the only reason it would be different is that somehow down at the base it behaves a little differently than Fibonacci. I mean, Fibonacci of 1, what is Fibonacci of 1? Is that 1 or 0? Is it 1? It's 1. But actually, you said 1? Okay. But actually, what does it take to compute opt of 1? It's no calls, because we just have it returning. So it could be slightly different, but the growth, the essential growth of the number of calls is behaving like the Fibonacci series. Now, what is f of n? Anybody know? Or approximately? I mean, does it grow slowly or rapidly? Yeah.
Looks like 1 plus square root of 5 over 2 at the end.
1 plus what?
Square root of 5 over 2.
Square root of 5
All that
over 2 to the n. Yeah, that seems vaguely reminiscent.
It's also plus 1 minus square root of 5 over 2 to the n.
Okay.
But that's
Anyway, exponential. The n is in the exponent here. So we have something here, and this is very rapid growth. Okay? So exponential growth. Certainly it's bigger. F of n is bigger than 2 to the n. Well, this isn't bigger than 2 to the n, is it? No. This isn't bigger than 2. But all right, it's exponential. Very rapid growth. And actually, figuring out this closed form is sort of a classic exercise in many math classes. Remembering it is not, but thank you for remembering what it is. So it's exponential, and therefore, if you did write up the program this way and then try to compute what f of 200 was, you're going to be generating a huge tree of recursive calls and waiting a very long time before you get your answer. So again, you could program this up in 5 minutes in any recursive programming language and try it out and tell me how long it takes to wait. Well, so that's not adequate. That's not what we want, although it's certainly a step. It's progress because it is a method. We have seen recursively how you can solve this problem, so we somehow have a logical understanding of the problem. It's just that the implementation as a recursive program is quite expensive. Now, just thinking informally, not formally in terms of that Fibonacci series, what's really causing the inefficiency here? Why is this taking so long? Yeah?
We're having to call off the function at the same time or a bunch of different times for the same numbers.
Yeah, it's very, very redundant. We're calling opt with the same value in here as a parameter many times. And you could also figure out how many times you're calling opt of j in this example. In fact, if you have n intervals, how many different kinds of calls are there? Different kinds of calls, not how many different calls. How many? Not what's the total number of calls, but how many different calls are there? Yeah, just n minus 1, or n, or whatever. You know, you can say opt of n, and then you're going down to opt of 1, but you don't. That's not a call. So yeah, there's n minus 1 different calls. You're calling opt of n minus 1, all the way down to opt of 2, and yet the total number of calls is growing exponentially when, in fact, the total number of different calls is just linear. So a very small number of different calls, but a huge number of a very small number of different types of calls, but a huge number of actual calls. So a huge number of calls, but only n minus 1 different types of calls. So huge redundancy. Opt of 4 is called here, and then not called again. Okay, opt of 3 is called here, and then opt of 3 is called again, and opt of 2 is called here, and here, and here. And again, if you, this sounds like a very good homework question. For this example in terms of n, how many times does opt of j get called? Okay, so you could think about that. Well, we actually have the answer. It's already, I mean, it's... Okay, so if opt of n is, well, anyway. So that's very inefficient. So a very immediate solution to that is what's called memoization. Okay, so here's the recursive program. Here's an example. Oops. Well, we have the recurrence over there. So a solution memoization. Not memorization, memoization. I think I once asked people in class to try to figure out where this word came from, and there's actually an answer. But to me, it's just some awful word that somebody made up. Anyway, memoization. And memoization basically is a technique that can turn any recursive program like this into a much more efficient, it's an implementation. Not always dramatically, but it depends on what's the level of redundancy. But always a good idea to extract out, reduce the redundancy. And here's the basic idea, or one way of playing this. When you think of this as a recursive program, this recursive, the call of opt5 makes these two calls. Okay? But you only really do one at a time, and you're going to stack the other one. So opt of 5 might actually call opt of 4 and puts opt of 3 on a stack. And you know, when it pops back up to here, it's going to then call that one. And opt of 4 might call that. So, or you could do it breadth first or depth first. Everybody know what I mean? I'm kind of rushing now because we're towards the end of the hour. But there are many different choices for how you're actually going to make these subcalls. So the first thing in memoization, the easiest way of doing this is make the calls depth first. Okay, so we're going to implement the calls depth first, which probably, well, it's probably the way, if you just wrote your program in sort of the obvious way, the recursion would implement it depth first anyway. Actually, this wouldn't because it's, anyway. Yeah. So opt5 would call opt4, opt4 will call opt3, opt3 will call opt2, opt2, opt1, pop back up here, do that, get the answer, pop up there, do that, and so on. So you're going to do depth first traversal of the recursive calls. Then, when any opt j is actually computed or actually known, put it in a table. In this case, indexed by 1 through n minus 1, or 1 through n, whatever. So again, just looking at it this way, opt5 calls opt4, calls opt3, calls opt2, calls opt1. So we have that value. Opt2 is either opt1 or it's the value of 2, whichever the best of that is. Now we know what opt2 is, and actually we also knew what opt1 is. So these could be put in a table. We actually, if you do the recursive calls this way, when you pop back up to this call of opt2, you actually know what the value of opt2 is. And then when you pop back up here, and then you go down and call opt1, you compare these two appropriately, and you know what opt3 is, and you put that in the table. And you come back here, and you have opt4, and so on. And what do we do with that? When the recursive algorithm is about to call opt_j, instead of just automatically calling it, it checks if opt_j is already in the table. If it's already there, you know the value. You don't have to do all those recursive calls. You've already got the value, so you can use it in the computation. Otherwise, you actually do the recursive call. Okay, I've run out of time. If you think about it, you only do n minus 1 recursive calls, because you're only going to call any opt_j the first time you see it. The fact that you're doing depth first traversal means that the next time you would think about calling it, you've already got its value, and you don't need to. So this turns an exponential computation into a linear time computation. Huge, huge improvements. And the memoization is easy enough to program too, so you could see this very dramatically if you wanted to. Okay.